Mastering supervised learning. Machine learning's dirty secret: not all learning is created equal. Where can one find the key distinctions between supervised learning, which involves training a model on labeled data to make predictions, and unsupervised learning, which focuses on identifying patterns in unlabeled data, as well as reinforcement learning, which involves an agent learning through trial and error? And how do these differences impact the performance of each approach in real-world applications? The eternal quest for wisdom in the realm of machine learning. As I sit here, surrounded by notes and coffee stains, I am reminded of my own journey to understand the intricacies of supervised learning, unsupervised learning, and reinforcement learning. It began with a problem, one that I'm sure many of us have faced: how to make sense of the deluge of data that threatens to engulf us all. In my case, it was a client who wanted to improve their customer service chatbots. They had a wealth of customer interactions, but no clear way to categorize or make sense of them. That's when I stumbled upon supervised learning. The concept was simple: take a dataset, label it, and train a model to make predictions based on that data. I thought to myself, this is the answer to our chatbot woes. And indeed, it was. With supervised learning, we were able to train a model that could accurately categorize customer inquiries and respond accordingly. But as I dug deeper, I began to realize that supervised learning was only half the battle. What about the cases where we didn't have labeled data? What about the instances where we wanted the model to discover patterns on its own? That's when I discovered unsupervised learning. Unsupervised learning was like a breath of fresh air. It was like watching a child explore a new playground, unencumbered by preconceptions or biases. The model was free to roam, to discover, and to learn, without the constraints of human labels. I remember the thrill of seeing a clustering algorithm identify hidden patterns in the data that we had never noticed before. And then, there was reinforcement learning. The thrill of the unknown. Reinforcement learning was like watching a child learn to ride a bike. The model stumbled, it fell, but it got back up again, each time adapting and improving. It was as if the model was learning through trial and error, just like we do in real life. As I delved deeper into each of these approaches, I began to notice the stark differences between them. Supervised learning was like a precision-crafted Swiss watch, each gear meticulously designed to perform a specific task. Unsupervised learning was like a jazz improvisation, spontaneous and freeform. Reinforcement learning was like a game of trial and error, where the model learned through experience. These differences, I realized, had a profound impact on the performance of each approach in real-world applications. Supervised learning excelled in domains where the data was well-structured and labels were abundant. Unsupervised learning shone in areas where patterns were hidden and waiting to be discovered. Reinforcement learning thrived in environments where exploration and adaptation were key. As I look back on my journey, I am struck by the humbling realization that each approach has its own unique strengths and weaknesses. There is no one-size-fits-all solution. The key is to understand the problem, to empathize with the data, and to choose the approach that best suits the task at hand. And so, as I sit here, surrounded by the detritus of my research, I am reminded of the wisdom of the great machine learning sage, who once said, "The best approach is the one that gets the job done." The key distinctions between supervised learning, unsupervised learning, and reinforcement learning lie in their underlying objectives, data requirements, and learning mechanisms. Understanding these differences is crucial to selecting the most suitable approach for a particular problem and achieving optimal performance in real-world applications. Supervised learning. In supervised learning, the primary objective is to train a model to make predictions on new, unseen data based on labeled examples. The model learns to map inputs to outputs by minimizing the difference between predicted and actual outputs. The availability of labeled data, where each example is paired with a target or a response variable, is the hallmark of supervised learning. This approach is further divided into two subcategories: regression and classification. In regression, the goal is to predict a continuous output variable, such as stock prices or temperatures. In classification, the objective is to predict a categorical output variable, such as spam versus non-spam emails or product categories. Supervised learning has several advantages, including high accuracy and reliability, especially when the labeled data is abundant and of high quality. Ability to learn complex relationships between inputs and outputs. However, supervised learning also has some limitations, such as required large amounts of labeled data, which can be time-consuming and costly to obtain. Relying heavily on the quality of the labeled data, which can lead to biased or inaccurate models if the data is flawed. Unsupervised learning. Unsupervised learning, on the other hand, involves identifying patterns, relationships, or structure in unlabeled data. The goal is to discover hidden insights or groupings in the data, such as customer segmentation or anomaly detection. Since no target or response variable is provided, the algorithm must find meaningful representations or clusters in the data. Unsupervised learning is particularly useful in exploratory data analysis, where the goal is to understand the underlying structure of the data. Identifying novel or unexpected patterns in the data. However, unsupervised learning also has some limitations, such as lacking clear evaluation metrics, making it challenging to assess the performance of the model. Requiring careful feature engineering and pre-processing to ensure the algorithm can identify meaningful patterns. Reinforcement learning. Reinforcement learning combines elements of supervised and unsupervised learning. The primary objective is to train an agent to take actions in an environment to maximize a reward signal. The agent learns through trial and error by interacting with the environment and receiving feedback in the form of rewards or penalties. Reinforcement learning is particularly useful in robotics and control systems, where the agent must adapt to changing environments. Game playing, such as chess or Go, where the agent must learn to make optimal decisions. However, reinforcement learning also has some limitations, such as requiring a large number of interactions with the environment to learn effective policies. Suffering from the curse of dimensionality, which makes it challenging to explore and learn from high-dimensional state and action spaces. Impact on real-world applications. The choice of learning approach significantly impacts the performance of a model in real-world applications. For instance, in image classification tasks, supervised learning has led to remarkable breakthroughs, enabling applications like self-driving cars and medical image analysis. In recommender systems, unsupervised learning can help identify user clusters and preferences, leading to more accurate personalized recommendations. In robotics and game playing, reinforcement learning has enabled agents to learn complex behaviors and achieve superhuman performance. In conclusion, understanding the key distinctions between supervised learning, unsupervised learning, and reinforcement learning is crucial for selecting the most suitable approach for a particular problem and achieving optimal performance in real-world applications. By recognizing the strengths and limitations of each approach, practitioners can develop more effective models and drive innovation in various fields.